Welcome to another session on equilibrium. In this video, we will discover the solubility product, precipitation, and the role of common ions and the solubility of sparingly soluble salts. Let's learn about the solubility equilibria of sparingly soluble salts. But firstly, what are sparingly soluble salts? As the name suggests, some salts dissolve only slightly in water and are called sparingly soluble salts. Although their solubility is low, a small amount does dissolve and establishes a dynamic equilibrium between the undissolved solid and its ions in solution. Example, barium sulfate solid in equilibrium with barium 2+ and sulfate 2-. At equilibrium, the rate of dissolution is equal to the rate of precipitation. Let's explore the solubility product Ksp. The solubility product Ksp is the product of the molar concentrations of the ions, each raised to the power of its stoichiometric coefficient at equilibrium. The solubility product only applies to sparingly soluble salts. Applications of solubility product. When two solutions are mixed, the product of ionic concentrations, called the ionic product, IP, is compared to Ksp. If IP is less than Ksp, the solution is unsaturated, no precipitation. If IP equals Ksp, the solution is saturated, equilibrium exists. If IP is greater than Ksp, precipitation occurs. Let's shift our attention towards common ion effect on solubility. Adding a common ion decreases the solubility of a salt. This happens because adding the ion shifts the dissolution equilibrium backward according to Le Chatelier's principle. Example, passing hydrogen chloride gas through a saturated sodium chloride solution causes precipitation of sodium chloride because the addition of chloride ions suppresses the solubility of sodium chloride. This principle is used in gravimetric analysis, where specific ions are precipitated as sparingly soluble salts. Examples include silver ions as silver chloride, ferric ions as ferric hydroxide, barium ions as barium sulfate. The solubility of salts of weak acids like phosphates increases at lower pH. This is because at lower pH, the concentration of the anion decreases due to its protonation. This in turn increases the solubility of the salt so that Ksp is equal to Qsp. We have to satisfy two equilibria simultaneously. Imagine a salt that gives the anion X- in water. This X- can combine with hydrogen ions to form the weak acid HX. Now, at lower pH, there are more hydrogen ions in solution, so more X- gets converted into HX. That means the amount of free X- goes down. To balance this, more of the salt must dissolve. That's why the solubility increases as pH decreases. We start with the expression for the acid dissociation constant K. K equals concentration of H plus multiplied by concentration of X minus divided by concentration of HX. Rearranging this, we get concentration of X minus divided by concentration of HX equals K divided by H plus. Now, take the inverse of both sides and add 1. We get concentration of HX divided by X minus plus 1 equals H plus divided by K plus 1. Now, combining terms, Hx plus X minus divided by X minus equals H plus K divided by Ka. Let's define a term F, the fraction of the total anion that remains as free X minus. So F equals X minus divided by X minus plus Hx. Substituting the earlier expression, we get F equals Ka divided by Ka plus H plus. As H plus increases, meaning as pH decreases, F becomes smaller. Let's say the solubility of the salt is S. Then Ksp equals S multiplied by Fs, which gives us Ksp equals S squared multiplied by F. Solving for S, we get S equals square root of Ksp multiplied by H plus K divided by Ka. So finally, solubility increases when H plus increases, or in other words, when pH goes down. We hope that you have understood the topic. You can now study chapter notes, watch video lectures, and solve MCQ tests of this chapter on EduRev to ensure you score well in your exams. And that's not all. You also get amazing courses for maths, science, English, Hindi, and much more for NEET. Thank you.